Alright guys, you're welcome to our next tutorial on deep learning series. Today we shall be looking at activation functions. Activation functions are very important in deep learning, and it's good enough for us to also understand how it works. So shown here is a typical example of a neuron, an artificial neuron. You have this as the node, which is also referred to as the neuron, and you have a set of inputs coming in, and each of those input is the weight multiplied by the input. So for here we have x1, x2, x3 are the inputs, which could be an image, or it could be a text, it could be an audio. And so you have the input multiplied by the weight that we're trying to learn, in this case W1, W2, W3. So at this node which actually performs the computation, is also referred to as the computational unit. What happens here is that we take each of the input, multiply by its corresponding weight, which gives us this, and we add a bias to that layer, which is B. Then once we're done with that, then for this particular neuron to fire, we need a function that will decide when it fires. So we pass the result of this computation through a function as is shown here, and this will decide whether this neuron fires or not. So this function through which we pass this expression is referred to as activation function, and there are various varieties of the activation functions. So let's look at them in details. And these are examples of activation functions. So you have sigmoid. X is our input. In this case, our x will be the whole of this in bracket passed to the sigmoid, and what it does is it uses this formula to compute the output. So this formula is used to compute the output, and you will discover that by the time you take consecutive values, and you can try that, say your x starts from -10 and goes up to +10. By the time you feed in these values of x into this formula and you plot it on this graph, you will get something like this. Let's take, for instance, if you take your x to be equals to 0, so x equals to 0, and you can use our calculator to see what e raised to power 0 is. What is e raised to power? That is -0. That will be 1 over e raised to power 0. You can do that using a calculator. I'm just trying to check that on my, let me see, I'm able to calculate that. I don't have a scientific calculator here, but if you check that, let me see if I'm able to bring a calculator out to do that for us in a moment. It's interesting to see that, just for us to have a look. And let's see my calculator. So okay, I'm bringing out the calculator out. Let's see. So let's bring the calculator out here. So let's see, e raised to power 0. So this is e that is 1. So because you have a 0 here, this is 0, by saying e raised to the power 0 gives us 1. If you want 1, e raised to the power 1 gives us this. So where are we? So e raised to the power 0, it gives us 1. So 1 plus 1 gives us 2. By 1 divided by 2, that will give us 0.5. So when our x is 0, the value will be 0.5. Let's take here, when x is 10, using our calculator again, when x is 10, so we say our x is 10, we take the e, it gives us this. So the formula says that 1 over this, so by the time you do 1 over that, 1 over this, 1 over x gives us this, and you add 1 to it, plus 1, and it gives us this, and by the time you now divide this one by 1, so this is our denominator. So by the time you say 1 divided by this will give us 1, just to tell us that this is going to be 1. So that is for the sigmoid. For tan h, which is another one, the formula goes thus, that it varies from -1 to 1. So if you enter the value of your x to be 0, it will give you 0, and if the value of your x is -10, it's going to give us -1. ReLU is very computationally cheap to compute. It just returns the value of the input, that is x, unless the input is less than 0. When the input is less than 0, then it returns 0. As you can see here, anything less than 0, if we trace it on the plot, the blue plot, it gives us 0. But anything from 0 onwards, it just returns it. So if we give it 0, it gives 0. If we give it 1, it gives 1. If we give it 10, it gives 10. Leaky ReLU is just a slight modification of ReLU. Instead of just giving us 0 on the negative part, it multiplies anything less than 0 with a small factor. This is another form. This is max out, and this is ReLU. So let's look in details. Like we said, this squashes whatever input that we give it. It squashes it between 0 and 1, just like we said. What are the problems with sigmoid? The number one problem with sigmoid is the saturated neurons kill the gradient. Now, as you know that activation function is just one of the important pieces in computing the neural networks. You have to do what you call error back propagation, and to be able to do error back propagation, you do what you call the partial derivative, the derivative of the total loss with respect to the weights in the network. Now, when you're doing this derivative with respect to the weight in the network, you discover that by the time you are doing the differentiation and you have the same values, for instance, in this area, irrespective of whatever values you put in, whether you put 20, 100, 1000, it just gives us 1 here. And here too, whether the input is minus 1 million, minus 100 billion, it just gives us 0 here. So no matter what we differentiate, as a result of constantly giving us just 1 or just giving us 0, it kills the flow of the gradient. That's what is being explained here. You do an error propagation with respect to the output of the sigmoid, and this is the derivative when you do the derivative of the output of the sigmoid. You can see here that everywhere that you have 1, the derivative is 0, and everywhere where you have negative numbers, as in everywhere where you have on the sigmoid where the output is 0, you see that the derivative is 0. So in these regions and in this region, the derivative is saturated, is killed. So another problem is the sigmoid outputs are not zero-centered. Now, as we can see here, that the output from the sigmoid, you see in this place we have this curve, this function passes through is 0.5, so it is not passing through is 0, so it's not zero-centered. So what happens to the gradient on W? All positive or negative number for a single can help. And what happens? Okay, always all positive or all negative for a single element mini batches can help. So that's just to explain what we meant by the gradient that we mentioned before. You allow gradient update in the directions, allow gradient update in the direction talking about what we mentioned, Q gradient, and it's not centered. Another problem is, of course, exponential is relatively expensive compared to other, like we just showed using the calculator. So we shall continue from this one, tan H. Thank you.